Right, so Martin asked me to talk about event processing, making sense of the fire hose in real time. I suddenly realized yesterday that people may think I'm talking about Twitter because they talk about the Twitter fire hose, but it's nothing to do with Twitter, so apologies if that was what you were expecting. Now, it is a comedy club, and most of the all of the previous speakers have had the wisdom of not telling any jokes, but I do live demos, so, you know, in for a penny, in for a pound. And actually, this is very relevant to both my talk, which is a little bit about time, but Jonas's talk as well. You probably heard this. The past, the present, and the future walked into a bar. It was tense. Well, I've got a little bit of a laugh, so thank you very much. Okay, so I'm Andy Piper. This is not Andy Piper. This is Alex Alves. He is an expert on event stream processing. He was asked to talk, and he couldn't make it. He was making money for Amazon or something. So that's not me. This is Andy Piper, but this is not me. This is the other Andy Piper. We actually work in very similar fields. It's very, very confusing. He works for Twitter. He works on sort of real-time messaging a bit, but that's not me either. This is me. I'm CTO at Push Technology. We have a real-time messaging middleware product, particularly over mobile. I used to work for Oracle. I ran their CEP product, which is why I have some knowledge about the subject I'm going to talk about. I used to work for BEA in this fair city in Montgomery Street on WebLogic Server. Very fond memories of that. I've contributed to Spring. I don't know whether I should admit that or not. It's difficult to tell in the audience. I've contributed to a number of standards, and I actually have a PhD in MapReduce, of all things, although I didn't make any money off it, unfortunately. But as Roland pointed out, I am the doctor. This is the running joke I have with the other Andy Piper, who doesn't have a PhD, and we have this sort of Doctor Who theme going on. So anyway, if you're not British, you probably don't really understand that. Okay, so agenda, Twitter style. I'm going to talk about what event processing, event stream processing is, what it isn't, why you might want to do it, a little history, how you measure things when they're sort of unbounded, how you use windows, how you use queries, how you go fast. It should say resiliently here, but then that would take me over 140 characters, so I'm going to put reliably here. How you do it in a distributed fashion, and then putting it all together, distributed and going fast, and with a combination of big data to close with. So, what is event stream processing? There are, you know, could almost take your pick, very generic words. I quite like this picture. Event stream processing is generally about dealing with a lot of data that's moving very fast, and your ability, or not in the case of this gentleman, to cope with it. So a couple of things that it isn't, at least, you know, in my definition. It's not stream processing in terms of being focused on local parallelism, you know, Java util stream, that sort of stuff. I have some opinions on that, but they have got me in trouble before, so that's not what we're going to talk about, none of these things. It's also not event passing. So event passing is where you pass events from A to B, and all you're doing is exchanging information. So things like JMS, messaging systems, those sorts of things. They are typically characterized by being very stateless, and that's not what I'm going to talk about either. It's also not brokering, sort of service buses, those sorts of stuff, which is event mediation, where you're typically filtering things, routing things, enriching things, that sort of stuff, but it's still stateless. So it's not that either. So what is it? So I looked in the font of all knowledge, Wikipedia, and actually it came up with quite a good definition, which I rather like. So I'll just read it out to you. Event stream processing deals with the task of processing streams of event data with the goal of identifying the meaningful pattern within those streams. So it's about querying data in data streams. And so you're looking for something, And the problem with what you're looking for is that the data you're looking in is not standing still. You know, so the proverbial needle in the haystack, but the haystack is moving. And also, the answers that you expect depend on multiple events. You're looking at history as well as sort of current time. And this means that the process is extremely stateful, so not stateless like the other things we looked at. But this is where all the interesting questions and answers are. So to use a sort of meta-analogy, this is a scramjet, which I believe they launched from sort of relatively close to here, somewhere on the Air Force Base on the West Coast. NASA has described producing thrust with a scramjet as compared to lighting a match in a hurricane and keeping it burning. Event stream processing is a little bit similar. You've got a hurricane, and actually you're looking for a needle in a haystack in a hurricane. Another way to look at it is like an inverted database. So with a traditional database, you have a bunch of static data, and you fire queries at that data, and you return results. So the data is not moving, but the queries are changing. In sort of event stream processing, CEP, you're inverting it. The data is now dynamic, and the queries are static. So you're actually firing data at the questions that you're trying to ask. OK, so all well and good. Why bother? Why do stuff like this? Why not use a traditional database or data store of some description? Well, if you think about recording the wind speed and direction in my garden, say. You have a weather vane, you attach it to some sensor, you pull in that data. So how much data is that? Rhetorical question. The answer is too much data, because when you're dealing with time, data is effectively infinite. You know, as time progresses, certainly that sort of sensor information just keeps accumulating. And it's one of the reasons why there are no perfect logs to Roland's question of yesterday. Another reason not to use a database is that time is integral to the questions that you're asking. So time is relevant, is in the data, it's in the question. And also the data is moving too fast to make it reasonable to approach with traditional database type technologies. And they tend to assume static data sets, and that's definitely not the case with event stream processing. So how have people approached this in the past? Well, there's been two schools of thought. The first school of thought is you take a database and you add some sort of time dimension to it, and that works pretty well. The other school of thought is let's take some sort of logic rules and apply time constraints, sort of more of a programming approach. And over the years, apologies for this is sort of one of two slides with extremely small fonts, but I wanted to get all the references in here so that when the slides appear later, you'll have access to them. So there are a number of things over the years that people have done, either on the logic side or on the database side. Tapestry is one of the very early incarnations of the sort of inverted database, not to be confused with Apache Tapestry, which is something completely different. Materialized views in '95, you can imagine if you are putting a sort of view layer on top of relational data that's changing, you sort of have to address the similar sorts of problems of how do you query data that's moving. And then in 2001, there was this book, Power of Events, written by David Luckham, which sort of takes a logic-based approach, and he actually coined the phrase complex event processing. He built some technology around that. He sold that technology to Avaya, and they actually use it in their sort of telecom systems today. Then at Berkeley, Michael Franklin did some work on the sort of database side of the house. He took Postgres, added some time dimensions to it, came up with Telegraph CQ. And then perhaps most familiar, a bunch of technologies, but in particular, the work that was done at Stanford under the Stream project, which is definitely sort of taking database and adding time dimensions to it. OK, so a couple of quick definitions here. So typically with event stream processing, you're dealing with streams of tuples or tuples, which is a multi-set of elements. I didn't actually know this, but a single tuple is actually a monad. And if Eric Mayer was here, he'd be jumping up and down with delight. completely irrelevant to this talk, but I just thought you'd like to know that fact. So an event stream or a data stream is an ordered pair of an unbounded sequence of tuples and an unbounded sequence of positive real-time intervals. And those are two of equal length. But the key thing here is that it's unbounded. So typically, when you're considering these sorts of systems, you have to assume that data is infinite. You can't assume that data is finite. So event stream processing is taking event streams, transforming them into new event streams through some sort of query or operator. And the outputs and inputs are continuous, and the operators are therefore continuous themselves, and therefore said to be operating continuous queries, which is a phrase I'm sure you will have heard of. So, okay, so if event streams are unbounded, how do you measure infinity? Seems like kind of a hard problem. Well, yes, it is. So what sort of simplifying assumptions can you do to address the problem of measuring infinity? Well, the first thing you can do is nothing at all. So just if you treat streams of events in isolation, if you process events in isolation, you don't have to consider the fact that the stream is unbounded. But if you remember, I said that was just event passing. It's not very interesting, not a very interesting problem. So another thing that people do is use synopses. So you store summary information about the stream of information flowing through your system. And you can imagine with certain types of data sets, that's very appropriate. For instance, consider music. You know, we all listen to MP3s on our iPods, and that's converting sort of sound information into more of a summary information sort of via compression. And with certain types of data sets, it's possible to do that. So you can actually operate queries on synopses rather than on the data itself and sort of break the problem down that way. But the most common thing that people do is use windows. So they basically define a working set over a stream of data, and the working set is what they work with. It's how they make the problem tractable. And for example, if you want to find continuous average, you can do that over the last n items in a data stream, and where n is, n is essentially your window. Put that over there where I can't mess with it. So if you think about it, it's a little bit like how do you chlorinate water in a pipe? So you've got water running through a pipe. How do you purify that? That's kind of a tricky problem. How do you make sure you mix it all up? Well, one way to approach it is you pipe the water into a bucket, essentially. You pour your chlorine in the bucket and then you pipe it out again. And although you have a sort of continuous flow of water through that system, the fact that you've sort of got this bucket of water that's effectively standing still in a way that you can deal with makes the whole problem more tractable. So people deal with different types of windows, the most obvious being sliding windows, so where basically you're sliding the window of interest over the data, or rather the window's standing still and you're sliding the data through the window because it's the data that's moving, remember. Other types of windows are jumping or batching windows where you look at a set of n elements and then you look at the next set and the next set and so on. More interesting windows are partitioned windows. So for instance, not all of the information in your data streams is related to each other. And in actual fact, you actually want to query information that's related rather than information that's unrelated. And you can use partitioned windows for that. So in this example, we've got a stream of U's and V's, and we're partitioning into U's and V's and then running our queries on each. And then most obviously, time-based windows. So these are sort of perhaps the most interesting windows. And there are others, but I won't get into that. OK, so we use windows to define a working set. So the scope of interest, what do we do with that? Well, we run queries against that working set as it changes, continuous queries, as I mentioned before. Well, what does that actually mean? I mean, when should you run queries? When is the right time to run queries? So I don't know whether this is technically correct, but it's a way of representing it. So I've said that you want to run queries when the output is not idempotent. So when the output is going to change. When you know that the output is going to be something different, that's when you want to run queries. But that's kind of a hard problem. That's sort of chicken and egg. How do you actually figure that out? When is that? Well, it might be when the contents of the window changes. It might be, or it might not. It might be when time simply progresses. You know, time ticks by and actually you want output that varies with time. It really depends on the kind of windows that you're using and the kind of questions that you're asking. And for me, this sort of gets at the heart of event stream processing, of CEP, because what you're trying to do is link cause and effect in an efficient manner. And it's one of the reasons why the answer is not simply programming. There's some sort of tough challenges here in terms of causality of inputs to outputs. Not from a conceptual point of view, but just from a sort of operational point of view, making the whole thing work and work efficiently. So how do we define windows? Well, I'm sort of from the extend SQL side of the house. And the way you can do this is by writing extending SQL, typically SQL 99, where you can query streams rather than tables. And here is an example. And you know, if you want to know more, there's a good paper here from the Stanford crew about not only how you compose these queries, but how you sort of execute those and in an efficient manner. And this sort of syntax can be applied to windows. So we've got some examples here for sliding windows, partitioned windows, time-based windows. I'm not going to get into the details, just suffice to say that there are ways of representing these things in a well-structured and precise manner. Okay, so that's how you run queries. So how do you make things go fast? Well, generally, in memory is the only way. So typically there's too much data, it's moving too quickly, and the only way you can process it efficiently is to process things in memory. And therefore, the obvious thing to do is operate as a gigantic state machine. Todd talked about state machines a little bit yesterday. You basically want to respond to changes in input to produce changes in output. Essentially, you want to go reactive. And if you want to do it really fast, then you can engage someone like Martin to sort of help you optimize your code or whatever. So why do we want it to be fast? So Martin was asking me, why aren't you talking about reactive streams? And I sort of gave some sort of wishy-washy answer. But thinking about this a little bit more, this is not really the same as reactive streams. So reactive streams deal with sort of pushing back on upstream so that you're limiting the data coming through so that you can cope with it. But when you're dealing with time, that can cause some sort of causal paradoxes. And typically with these sorts of systems, you actually want to keep up. You want to keep up with the data flow, because if you don't keep up, then you just sort of get overwhelmed. And if you push back, then you're sort of making changes to the concept of time, Jonas's talk notwithstanding. So typically, if you can't keep up, what you do is you throw stuff overboard. And typically, you want to do that earlier. So you don't want to throw off overboard information that's relevant to you. What you want to do is throw away information that's irrelevant sooner, so that you can keep up with the sort of more interesting information. So you want it to be fast. You can make it fast by sort of taking a state machine approach. How do you make it resilient? Well, it's stateful, so that's challenging. Stateful systems are hard to make resilient, and in particular, the state here is changing really, really quickly. So how do you make it resilient in that sort of context? So there's a number of things that different people try. Jonas actually mentioned a couple of them in his previous talk. So one of the things that people do is basically save all the state. So they just stream everything to disk. When they have a failure, they replay all of that information, rebuild their state that way. But that's kind of a problem if data is infinite. I mean, can you save all of the data for all time? Generally not, but in some cases it does work, because this data is generally append-only. You can stream it very quickly to disk. If you look at things like Kafka, they do that very efficiently, and they're sort of striping across multiple disks. So people do that, but there are challenges there when you're dealing with effectively infinite data. The other thing you can try and do is save the state of your state machine. But again, that's challenging because the data is, the state is changing very, very rapidly. And generally, it's changing too rapidly to be effective. So another thing that people do is a little bit of both. So they sort of checkpoint state every so often and record a sort of set of streaming changes that they can replay against that checkpointed state. And this is what a lot of commercial systems do to make these sorts of implementations resilient. And then finally, the other thing that people do is don't record anything at all, basically run identical systems in parallel. If they're seeing the same streams of information, then they should be building the same sort of state model, and therefore, if one fails, another can take over. Problem with that is difficult to synchronize, and also it can be difficult to, if you get a node failure and you bring up a new node, how do you make it catch up with the sort of state of reality? Actually, it needs a sort of persistent view of what happened, and you end up finding yourself back at sort of recording stuff. So how do you scale these sorts of systems? Well, you do what everybody else does. You follow the crowd, you add nodes. These are Canadian lemmings. They're all being very polite after you. Hopefully that means more to the American. I think it was targeted at an American crowd rather than English. So you basically want to distribute the processing over multiple nodes like everybody else does with all of these different sorts of problems. And also, you might want to try and ingest information from multiple different sources at the same time. Obviously, if you're sort of trying to ingest everything through the same pipe, there can be some bottlenecks there. And there's various technologies, such as Flume, such as Kafka, that allow you to do these things. Although it does slightly depend on the information that you're ingesting being sort of independent in some way. If there's sort of a causal relationship between the information that's coming in, at some point, you're going to have to join, and you end up with a bottleneck again. So how do you distribute these sorts of systems? Well, if you can consider an event processing system as a directed acyclic graph of event streams, and inputs and outputs are event streams. And nodes are operators or groups of operators, and you can distribute the nodes and use the event streams themselves as communication links. I mean, kind of so far, so obvious. And there are actually tools that allow you to do this. Apache Storm is one of those. So it's a toolkit for creating distributed event flows. It deals with bolts and spouts as operators and sources, and you can put things together using a closure DSL. I think one of the things to pick up from this is if you look at big data things like Hadoop, MapReduce, they're definitely running batch-type queries. So they're asking a question, they're going away, firing for the results, bring back the results, job done. Whereas something like Storm, they're running forever. They're running continuously. And here's an example of the kind of closure DSL that you use for creating Storm topologies. So, okay, we've made it fast, we've distributed it, we sort of made it reliable. How do we put those things all together? How do we reliably distribute things? Well, we've got a bit of a problem here now, because now we've got lots of state. It's distributed across a bunch of nodes, and that makes synchronization tricky. The good news is that if you can preserve the relative order of information moving through your network, then the system can be deterministic. I had to introduce a Leslie Lamport quote here. Unfortunately, Jonas actually referenced the same paper, so damn you, Jonas. But, it's a very relevant to this, where it basically says that time doesn't matter so much as long as you preserve the relative order of things. And in theory, if you replay information through your network, you can rebuild the state of the network, as you can do for individual nodes. We talked about how we can rebuild state for an individual node by replaying information through that node, and you can do exactly the same thing for a network of processing nodes. You can try storing state for operators, but that kind of gets exponentially harder when it's all distributed and synchronization is a problem and so on. So In terms of sort of reliable distribution, there's been a bunch of research around this. And one of the things that people have sort of posited is that it's not actually always necessary to have precise recovery. So to Jonas's point about linearizability. So everybody thinks that they need precise recovery. So basically, if you have failures, there's no sort of external knowledge that a failure has occurred. But often that's not actually what you want, or not actually what you need. So there's a couple of different, in event stream processing, there's a couple of different types of recovery that people can also use. So rollback recovery, so you don't lose data, but you may actually get duplicate outputs. You may output the same information again, as sort of similar to messaging systems. And gap recovery, where actually you do lose data. And for certain classes of problem, that doesn't actually matter. You know, sometimes it's actually more important to just sort of keep up with the now than it is to preserve the past. And there's a bunch of other things that people do, in particular upstream backup. If you want to know more, highly recommend this paper, High Availability Algorithms for Distributing Stream Processing. And reactive streams has some relevance here as well, but I encourage you to read the paper. It's a bit too big of a topic to cover here. So how is event stream processing reactive? Well, clearly it's message or event driven. I mean, that's obvious, really. And we've talked about resiliency, how you make the system resilient. And continuous queries gives you this kind of responsiveness. So you're returning results as they happen, returning answers as they happen. So the system is sort of naturally, by design, responsive. Elasticity, though, is a little bit harder with these sorts of systems. You know, how do you, if you've got streaming data and you're sort of trying to manage the relationship between items in that data, how do you sort of add nodes to scale out? It's a harder problem. It's not one that I think people have addressed particularly well so far. So we talked about stream processing. What about data? So often there is a time dimension to data problems. I mean, obviously, okay? So, you know, there's lots of different problems you can think of where time is relevant. Also, there's often lots of problems where there's a data dimension to stream problems. So, for instance, think about BART or the tube in London. Let's say I want to know all of the trains that are running late. So I need 2 bits of information for that. I need to know about the times of the trains running as they are now. So there's sort of streaming information that's changing all the time. I also want to know what the timetable is, like when should they be running, when should they be arriving at stations. And that's a static data set. And to come up with the answers, who's running late, I need to join those 2 pieces of information. I need to join the static information with this streaming information. So that seems like an easy thing to do, right? I mean, it doesn't seem that hard, especially if you're doing it all in memory. And it is when the data set you're joining with is small. But when you make the data set larger, then things become a lot more problematic. How do you address that sort of problem? What can you do if your data set won't fit in memory? Can you cache it? You know, just retrieve the information that you care about, join with it in memory? Can you push queries down into the data store? It's a very similar problem to streaming with big data. So in big data, you're very familiar with the 3 V's of big data: velocity, variety, and volume. Anything where velocity is involved generally is a streaming type problem. And so often big data problems have a streaming element to them. And it is, by definition, big data is a very large problem domain. You're dealing with a very large data set. So how do you integrate that in a streaming system? And by the way, the data is now distributed, so you just sort of made the problem 10 times harder. So this is sort of a typical big data architecture, MapReduce, you know, Hadoop-based, and you have a question, you map the question across all of your distributed data, and then you kind of reduce the answer. And all very familiar to you, I'm sure. So the key thing about this architecture is it's very batch-driven, okay? So the way the questions are asked are batch. The way the output is recorded is batch. So it covers all of the data, but it's not even close to real time. So, you know, these sorts of queries can run for hours even or longer. So although big data is a tremendous tool for analyzing large amounts of data, it kind of falls short when you want to look at things in more real time, squidgy real time, as Martin would say, perhaps. So the way people address this is through something called fast data. I'm sure you've heard of it. I think also referred to as the Lambda architecture. And so what you want to do is big data is a given. You know, Hadoop is a given. Everybody's using it. There's no getting away from it. That's the way that people store that sort of information. But getting online access to some of the answers to those queries is a little bit tricky. And so what people tend to do is, if you can sort of break the question into two parts, so you're trying to run a query, and you want to run the same query against the static data set, but also the incoming stream of data, if you're dealing with streaming data, which we are talking about. And actually, if operations associative and commutative, you can actually do that. And some of the challenges with solving that sort of problem is in making the sort of batch Hadoop layer more accessible to these online systems. And so people typically add some sort of caching or indexing layer. And then on top of that, those sort of cached results, they then add some sort of incremental update, incremental query layer that can join essentially static results with incoming dynamic results. And it's a bit like the recoverable architectures that we looked at earlier. So you're taking snapshots and applying incremental updates. So there's sort of the same sort of concepts revolving around all of these problems where you're trying to join moving data and moving answers with some kind of static data and static answers. And the current state of your system is some known state plus some set of changes. And it requires these static queries as well as sort of online dynamic queries. And this is something that Spark does quite well. Spark sort of deals with RDDs, and basically it allows you to cache query results from Hadoop in memory and then apply sort of further queries to those cached results. And then there's also this thing called Spark Streaming, which sort of allows you to take that to the next level and do micro-batching across that streaming data. So some of the technologies that people use for this, Storm we obviously talked about. Spark talked about a little bit more, and that seems to be something that's really sort of taking off in terms of use and applicability. It's not, I've sort of termed it fast data-ish here, because what you really want is something that is outputting new information every time information comes in. So what Spark actually does is it does these sort of micro batches. So it looks at a set of data, and then it looks at the next set of data, and then it looks at the next set of the data. So you get sort of updates on a sort of repeating batch basis rather than on a continuous basis. Flume I've mentioned for fast ingest of log data, and Kafka is something similar as well. I was reading about Kafka on the plane over the way over, and this is a really, really cool technology where they basically say, you know what, we could actually save most stuff to disk. You know, disks are fast enough these days, and if you stripe across disks and you sort of manage your writes in such a way that they are, you're writing all the time, you can actually write a vast amount of information directly to disk and then sort of query against that. Hadoop streaming, I'll mention it in passing. I don't know whether people use that very much. And then some other technologies, Hive, Cloudera, Impala, sort of focused on online querying against sort of massive data sets, which is all sort of part and parcel of the same sort of problem. The thing I wanted to emphasize here is there are a lot of different choices. And I don't know whether you can read that. It says, for the love of God, there are too many words and not enough time. And these technologies are moving very, very quickly. People are inventing new ones all the time, and they sort of overlap in many different ways. And it's a really, really interesting space. So, in summary then, dealing with fast-moving streaming data can be like trying to light a match in a hurricane and keeping it burning. But this thing actually flew. I mean, it was for 5 seconds or something, but it did actually fly. So you can actually do it with the right sort of tools and technology. So what about the future? So this is not an area that's solved by any means, and people, you know, there's been a lot of research going on for a long period of time, and the whole sort of big data problem has made the whole thing much more complicated, but much more interesting as well. One of the things that really isn't cracked is sort of ease of use. For some reason, people have a hard time getting their head around how you query against streaming data sets, whether it's people have tried graphical approaches, they've tried the sort of SQL approach. Either way, it's hard to get your head around what you're actually doing. And the kind of queries that you run can get really, really complicated really, really quickly. And so no one's really solved the ease of use problem as yet. Plus, when you add distribution in, the whole sort of how do I understand this, how do I reason about this gets a lot more challenging. The good news is that Hadoop seemed to manage. This is a happy elephant, as you can see, basking in the water. So Hadoop managed it. It sort of managed to take a sort of hard problem and construct it in a way that people could get their head around and do real work with, apply it to real problems. A lot of research going on around fast data architectures. I've sort of really only scratched the surface here, but you can sort of see this whole problem about how you join sort of static data sets with moving data sets, and the optimizations around those is just a really, really fruitful area of research and a really hard problem to crack. And then what everybody really wants is online sort of machine learning, predictive analytics, that sort of thing. So it's not just about querying information as it comes in, it's about predicting what's going to happen in the future. And there's a bunch of technologies that looking at that. I just mentioned two here, Spark ML, machine learning library, and Hadoop technology. But this is where certainly a lot of businesses are very focused on this particular area. How do you predict what's going to happen in the future based on streaming data in the past? And then finally, there's a bunch of work going on around making querying stuff online just much easier and more declarative. And Hive and Spark are examples of those. So I seem to have spoken really quickly, and that is the end. Thank you.